And welcome everyone to today's MRS webinar presented by MRS Bulletin. So I'm Gopal Rao, the editor of MRS Bulletin. And typically each month, the theme topic of the month's MRS Bulletin issue is the topic of the webinar. But today's webinar is a little bit different and special. It's actually based on the MRS Bulletin special issue that was published in December of 2015, titled Materials and Engineering Propelling Innovation. So just some brief background to the issue in case you've not seen it, and I hope many of you or most of you have already seen a copy of this. The goal of this special issue was to capture the unique relationship between and the intertwining of materials and engineering. So materials enable engineering. Engineering, in turn, depends on materials to transform design concepts into physical entities. So this relationship really continues to grow as the societal demand for new products and processes is evolving and growing. There are about 20 articles in this special issue of the Bulletin, and that these include many different materials categories and the many interactions between material science and technology development. So, in essence, the overarching goal, I guess, of the issue is to stimulate dialogue and interactions between materials researchers and the people who actually use these materials and make products out of these. The guest editors of this special issue are V.S. Arunachalam of the Center for the Study of Science, Technology and Policy in Bangalore, India, and he's also associated with Carnegie Mellon University. Y.T. Cheng of the University of Kentucky, who will actually participate in the Q&A later in the webinar today. Dipankar Banerjee of the Indian Institute of Science, and Jim Williams of Ohio State University. So I really thank them for all of their efforts in putting this issue together. As Bob mentioned, the presentations that you're going to see today were recorded at the 2015 MRS Fall Meeting in Boston exactly 3 months ago, actually, on December 2nd. And in that session, we had 3 talks followed by a panel discussion. Today, we will present 2 of those talks by Colin Humphreys of the University of Cambridge, and Teresa Pollock of the University of California in Santa Barbara. This will be followed by a recreation of sorts of the very exciting panel discussion we had in Boston. And we are actually privileged to have 5 of the panel members from that session participate in the webinar today, including today's host and moderator. And they will answer any questions you might have. I do want to note that there is a similar session planned for the spring 2016 MRS meeting upcoming in Phoenix at the end of this month. So if you're attending the Phoenix meeting, please consider attending this session as well. So talking about the moderator, it's my distinct pleasure now to introduce W. Judd Reedy as the host and moderator for the webinar. Judd is the Deputy Director for Innovation Initiatives for the Georgia Tech Institute for Materials. He has a PhD in Material Science and Engineering from Georgia Tech. He's also an adjunct professor of Material Science and Engineering and a principal research engineer on the research faculty of the Georgia Tech Research Institute. Previously, he has worked for General Dynamics, which is like a large organization, a large company, as well as in small business with microcoatings technology. So his expertise and experience spans the spectrum of small companies to very large companies and university as well. So his research focuses on energy, aerospace, nanomaterial applications, and electronics reliability. Judd was a 2015 volume organizer for MRS Bulletin, and he's also a meeting chair for next year's MRS Spring Meeting in Phoenix. So he is very active with MRS. He has won a number of awards and I'll just mention the TMS, Electronic Magnetic Photonic Materials Division, named him as a 2002 Young Leader, and in 2015 he also received the Brimacombe Medal from TMS. He's also the recipient of the Innovative Research Award from GTRI in 2013, among others. He also happens to be a helicopter and instrument-rated fixed-wing pilot, and I don't know where he finds the time to do all of this, but I'm just happy that he agreed to be the moderator today. So, Judd, thank you for hosting the webinar today, and I'll pass this over to you.
Thank you very much, Gopal. And yeah, I actually don't really have much time anymore to fly my helicopters and planes around there, but every now and then I'll get up there in the air. But it's quite an honor to host and moderate this webinar. Greatly appreciate MRS reaching out to me to do this. And like Gopal said, it was a great session that we had at the last MRS meeting, and I really hope folks are able to attend the follow-up session that we'll be having here in just a few more weeks at the spring meeting. And so it's just with great pleasure that I get to introduce our two talks by Colin Humphreys and Teresa Pollock. Sir Colin Humphreys is a professor of material science and director of research in the Department of Material Science and Metallurgy at the University of Cambridge. He's also a fellow of Selwyn College at Cambridge, as well as a fellow of the Royal Society and a fellow of the Royal Academy of Engineering. He founded a spin-off company called CAMGAN. GAN is gallium nitride in this particular case, to exploit the research that he was doing, producing materials for low-cost LEDs. That company was acquired by a much larger company called Plessey, and now they're manufacturing LEDs out of Plymouth in the United Kingdom. You likely have either seen these bulbs on the shelves, or you may even have them in your house. He has won numerous prizes, so many that I won't name, except for the one that's probably the most impressive of all, and that's how he gets his first name, the Sir part. He was knighted for his services to science back in 2010. So that's obviously quite an honor for a citizen of the United Kingdom. Our second talk, and Colin's talk will be significantly focused on that gallium nitride technology. The second speaker is Teresa Pollock. I've known Teresa for at least a decade and a half now, it seems. She started her career at GE Aircraft Engines, but currently she's the chair of the materials department at University of California, Santa Barbara. She earned her PhD prior to that at Massachusetts, at MIT. She's also had academic positions on the faculty at Carnegie Mellon University, as well as the University of Michigan. She's a member of the National Academy of Engineering since 2005, as well as a TMS fellow in 2009. She also served as president of TMS, which is a materials research professional society, much like MRS is. Her current interests include mechanical and environmental performance of materials in extreme environments, unique high-temperature material processing paths, ultra-fast laser materials interactions, 3D materials characterization, and alloy design.
So the first speaker is Sir Colin Humphreys. He is from the University of Cambridge and is a professor of material science and director of research in the Department of Material Science and Metallurgy at the University of Cambridge. He's also a fellow of the Royal Society and a fellow of the Royal Academy of Engineering. He earned his PhD degree at the University of Cambridge with an honor, and then he was also lecturer in Oxford and Liverpool before he was coming to Cambridge. Beside this academic activity, he also founded and directs the Cambridge Center for Gallium Nitride, and he founded a spin-off company which is called CAMGAN, to exploit the research of his group on low-cost LEDs. So after selling this company, he is founded the Cambridge Rolls-Royce Center for Advanced Materials for Aerospace. And this center is now developing materials which are used in Rolls-Royce engines. So he also received many prizes. I will not list all of them, but for me very interesting is that he was knighted in 2010 for services to science. So it is really a fairy tale here. We have a real knight, and I would like to ask you to come on stage, please.
Well, thank you very much, Anke, for that kind introduction. Next time I'll come riding in my horse and you can share the ride. Thank you. Well, it's a great pleasure to be here and to talk about innovation. And I'll just mention on the very first special issue that Gopal mentioned on energy, I was a contributor to that, and that was a wonderful issue. And this innovation issue is a fantastic issue. I mean, look through the articles, they're just fantastic articles there. So do take your free copy and read it and digest it and learn from it. So I'm going to talk about this real case study. In 2014, I think most of us here will be aware that the Nobel Prize for Physics was awarded to the 3 Japanese scientists. And the citation said, for the invention of efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. So I think everyone was delighted to see this Nobel Prize going essentially to material scientists. And as an aside, there's no Nobel Prize for material science. That's terrible, isn't it? But there isn't. So you have to come in as a physicist or a chemist. But anyway, this Nobel Prize went through 3 Japanese scientists, and they did fantastic basic science and also exploited their science. However, what they did, which was fantastic, they grew GaN LEDs on 2-inch sapphire or less than 2-inch sapphire wafers. And the problem is that's still quite an expensive technology. So if we're really going to achieve widespread use of LED lighting, really widespread throughout the world and throughout the USA, then the cost has to be reduced. And so I'm going to talk about cost reduction and how innovative science and engineering can lead to that. This is from a United States Department of Energy report on GaN LEDs. And the first statement says, if you use GaN-based LEDs, you can reduce the amount of electricity used for lighting by 50%. And of course, you need to have has widespread uses of GaN LEDs to do that. There's this interesting comment also in the report. No other use of electricity has such a large energy-saving potential as LED lighting. It's a surprising statement at first sight, because at first sight you think, oh, if you make air conditioning more efficient, we save lots of electricity. If we make my electric toaster more efficient. And the reality is, things like air conditioning, electric toasters, heaters, dishwashers, clothes washers, they're already very efficient. To increase their efficiency by another 10% is very difficult. Lighting, as we'll see, is very inefficient. So the low-hanging fruit, to use that terrible phrase, is lighting. That's what this was identified by. The potential of GaN lighting. Lighting globally, and also in many countries like America, uses about 20% of all electricity. And if we use LEDs, as the DOE report said, we're poised to reduce that figure by 50%. So that means lighting will then use just 10% of electricity, so we will save 10% of all electricity. And in the UK, that amounts to about $2 billion per year, or £2 billion per year. I'll give the savings in the USA in a later slide. £2 billion a year. Think of as a pound as a dollar. That's a rough conversion rate. So these big figures are quite hard to realise. About 2 years ago, the UK commissioned someone called Dilnot to do a report, and the government asked him how much extra we would need to spend on old people to look after them really properly. So he did this report, and he said the additional funding should be about £1.5 billion per year. And this went to the government, and the Treasury threw up their hands and said, we can't afford that, and they sort of filed the report away, and it's disappeared probably forever. So if you had widespread use of LED lighting, you would save enough money to look after all the old people in England really properly. And obviously the same would apply very much to America. This is the wall plug efficiency of light sources. What we mean by wall plug efficiency is the real total efficiency. So you take a lamp, plug it into a socket, this is the efficiency. It takes into account not only the efficiency of the light itself, but also any driver electronics. So incandescent light bulb, just 5% efficient. You get 5% light out for the electricity you put in. Halogen light bulb, 7% efficient. OLED panel, 15%. A long fluorescent tube, 30%. Compact fluorescent lamp, 25%. White LEDs, 35%. And these are all products you can buy now, and that is their wall plug efficiency. And you see already white LEDs are the most efficient light source, and they're 7 times as efficient as an old-fashioned incandescent light bulb, for example. In the laboratory, we have white LEDs, which are 60% efficient, and they will be coming onto the market in the next few years. So when that happens, we'll have a light source which is 12 times as efficient as an incandescent light bulb, and over twice as efficient as a compact fluorescent lamp. So these are really efficient light sources. Global impact of LED lighting. If 40% of the world's lighting was LEDs, then we could close over 500 power stations. Why aren't we doing that now? And the main problem is cost, as I will repeat saying. And of course, if you have 80% of the world's lighting LEDs, then you could close 1,000 full-size power plants, full size being 1 gigawatt typically. These are some of the growth facilities we have at Cambridge. So we have a system which will grow on 6-inch wafers and a system which will grow on 8-inch wafers. So these are industrial scale growth facilities we have. This is the latest DOE report, May 2015, and it's a really good report. And what they did in this slide, they just went out into the shops and they bought different light sources and they measured the light output. So this is nothing to do with the running cost, this is the capital cost of the light sources. So they purchased LEDs, and the cost per kilolumen of light emitted is $10. They purchased OLEDs, and the cost was $800. They purchased, still although they're banned, probably old-fashioned incandescent light bulbs, and the cost is $0.6. For CFLs, it's $2. And you immediately see the cost reductions necessary. So although LEDs over their lifetime will save energy compared with OLEDs or incandescent or CFLs, not many people will go and pay $10 for LED replacement light bulbs. So we need to reduce the cost by typically a factor of 5 if we're really going to get the widespread adoption of LED lighting throughout the world. LEDs now are just 5% of lighting sales in the USA. I think it's increasing rapidly, but when they went out and they did the report, that was a 5% figure. And the reason, again, is the cost. They're just too high cost. And people buy CFLs because they're much cheaper at the moment. So what's presented with widespread use? Say it again, it's cost. And if we're talking now about innovation, then it's obvious what the solution is, what we have to try to do. There's a major market for reducing low energy products, and as a nation, as a world, we have to reduce our energy consumption. And to get widespread adoption, we have to reduce the cost. So that's the innovative challenge. How to reduce the cost of LEDs so that they really become used in a widespread way. So low power LEDs, as used in children's toys, very, very cheap. High power LEDs used for lighting are expensive. In the UK, it cost me a few months ago £15 to purchase a Philips 60-watt equivalent replacement LED. It's now down to £10. I think in America it's a bit cheaper than that, but still they're more expensive than compact fluorescent lamps. This is DOE predictions in that report for 2030. They say if LED costs do come down, so we can make that step, and efficiency is up, then they predict that 90% of the US market, 90% of US lighting in 2030 will be LEDs. And I think the same will happen in the world. So we really have a dominant light source in the world of LED lighting, but the costs have to come down to do that. Interestingly, the electricity savings, if this happens with LEDs, are twice that generated by wind, and they're 20 times that generated by solar. And the annual savings, and here's a figure in the report, the annual savings the US will make by having 90% adoption of LEDs is $40 billion per year. It's just huge savings, huge financial savings. And of course, there are no subsidies for LEDs, as there are with some other forms of power like wind power and solar. So don't look at all these figures. This is just saying the commercial markets for gallium nitride are very large. So if you look at the top figure, solid-state lighting market for GaN-based LEDs, over $100 billion. Slightly down on that slide, all market areas forecast to have double-digit market growth over the next 5 years. And you'll notice on that slide there's also gallium nitride power devices mentioned and RF devices. And again, those are low-energy devices. So for an equivalent power electronics device, if it's made from gallium nitride, it consumes about 50% less energy than if it's made from silicon. So again, for power, gallium nitride is not only low energy for lighting, it's also low energy for electronic devices. And at the moment, electronic devices are probably 5 years behind the lighting devices in the research and development phase. And right at the bottom, the key to delivering is reduced cost. So my group was trying to solve this cost problem, and the reason these devices are expensive is that the gallium nitride LEDs, they're grown on small diameter small diameter sapphire or silicon carbide wafers, typically 2-inch diameter. And that's how they used to be grown. To reduce costs, one thing we've been pursuing is to grow on 6-inch diameter silicon wafers. And you can instantly see that should reduce costs because silicon is cheaper than sapphire or silicon carbide. And also, if you grow on a 6-inch diameter wafer, the processing costs of that wafer are not very much more than growing on a 2-inch diameter wafer. And on a 6-inch diameter wafer, you get 9 times as many devices as you do on a 2-inch wafer. And because the edge effects are less, you actually get 10 times as many usable devices. So you can see where these cost reductions come in on growing on a large diameter wafer and also on growing on silicon. And if we can do that, we substantially reduce the cost of LEDs, and that will enable the widespread use. So the UK can save $2 billion a year, and £2 billion a year, and the USA can save $40 billion a year. And in the UK, we could close or not build 8 large power stations. And I'd like to acknowledge my postdoc, Dan Danjou, who pioneered the growth of these GaN LEDs on 6-inch silicon in my group. So, just to initiate our growth on silicon, when we started this work, all commercial gallium nitride LEDs were grown on sapphire silicon carbide. Our vision was to innovate and to grow on silicon. It all started with a 3-month exploratory grant I had in 2003 from the EPSRC, that's the UK Government Funding Council, which was called Exploratory Proposal to Grow and Characterise Gallium Nitride on Silicon, and it was just over £50,000. So that's how everything started, and we grew on 2-inch diameter silicon wafers then. And I'd like to thank and acknowledge this funding council, the EPSRC, for continuous support for my gallium nitride research since then. And that's really important. And for innovation, if you're in universities, it's really important that your government agencies fund you continuously to develop this, because we know in the materials area, development of products can take typically 10 years from start. And you really need that support to get through to the actual prototype device stage. So a message, to give to your funding council is really important. So why do we want to grow on 6-inch silicon? I've said some of the reasons already. Another reason is it's compatible with silicon processing techniques using a silicon foundry. So silicon has now moved to 12-inch, so that means there's a number of silicon foundries around which are 8-inch or 6-inch, which are totally depreciated and there for free to use if you have one of these. And the thing about using a silicon foundry is it's automatic and it has high yield. And the processing on sapphire wafers tends to be largely hand processing by comparison. And if we can grow on 6-inch, then we can probably grow on 8-inch and then grow on 12-inch for even larger cost reductions. So this gives a cost breakdown of package LEDs done by Yole Development in 2013. And if you look at the right-hand side, what you'll see is it's quite a complex situation trying to minimize cost. The cost of the substrate itself is only 11% of the cost of the packaged LED. So if you save on substrates itself, you don't save so much. If we look on the left-hand side, the cost of growing on 2-inch sapphire, the cost per millimeter of 2-inch sapphire is much the same as the cost per millimeter of 6-inch silicon. So as I said before, you get 10 times as many devices on 6-inch silicon than on a 2-inch wafer. And so you immediately get quite a large cost saving from that. The alternative is to try and grow on 6-inch sapphire, which again gives this reduction in unit cost. But you see 6-inch sapphire is about 10 times more expensive than 6-inch silicon. So if you have 6-inch silicon, you improve the substrate cost and save about 10% of the total cost by doing that. But you get much greater savings, it turns out, because if you grow on silicon, you can then enable cost reductions in the processing, in the packaging, and also in the phosphors. Now, I don't have time to deal with that, but just to say, if you grow on 6-inch silicon, you can then do chip-scale packaging rather easily and chip-scale optics. And this hasn't yet been applied in the gallium nitride area, but it's starting to be applied, and these will bring significant savings. And the company which is exploiting that technology, Plessey, which I mentioned, they reckon that the total cost reduction of a packaged LED grown on large area silicon is typically 5 to 10 times. So these are just the sort of large cost savings you need if these devices are going to be really cheap and compete with compact fluorescent lamps. So problems with the GaN growth of 6-inch silicon. The first one is cracking, because you grow at 1,000 degrees centigrade. When you grow the gallium nitride on the silicon, the thermal expansion coefficient mismatch is 52%, which is huge. The gallium nitride is in tension when you cool down, and it cracks. So you have to put in compressive stress when you grow deliberately to counter this tensile stress on cracking. The other factor is the dislocation density is very high when you grow on silicon, about 10 to the 10 per square centimetre, and we have to do dislocation reduction techniques. And those are both quite difficult, but they can be done. And we can now routinely grow gallium nitride LEDs on 6-inch silicon with no cracks at all and with relatively low dislocation density. And this is an example of the first fully processed LED on 6-inch silicon wafer in the world, which was, the growth was done by my group in Cambridge, and then it was processed by RFMD on a 6-inch processing line. And the left-hand side shows a 6-inch wafer, totally crack-free. There's a variety of different LED sizes on that, so it's a sort of test wafer. And then the top right-hand side shows a number of these LEDs of different sizes, and the bottom diagram shows a current being passed through the LED. It's actually emitting blue light that's so brilliant it's saturated the detector, so you just see it as white light. It's actually blue light being emitted. So how to exploit our research? Because it's all about innovation. So the first thing to say is it can be difficult and it can be tricky. And we started having a project with a company, UK company called Filtronic, and this project started in, I think, 2005, I think, or 2006. And they were going to manufacture LEDs in the UK, and after 18 months, they fell on hard times financially, and they had to sell half of their manufacturing facility to RFMD, an American company, and so they no longer were able to manufacture our LEDs. They sold off their processing lines. But RFMD took this project over and spent another 18 months on that, and as I said, they successfully processed that wafer I showed. But after 18 months, they fell on some hard times, and although RFMD in the UK wanted to continue with the project, the management team in the USA said it wasn't their core business, so they stopped the continuation. So those exploitation routes were closed. I then gave a talk in the UK, and someone from a company called XFab was there, and they said, oh, we'd love to manufacture this product. So they took it along, and they worked on processing for 6 months, and then their parent company, XFab in Germany, decided to close the UK factory. So we tried the sort of conventional routes for exploitation, or a conventional route going through other big companies, and we kept hitting these brick walls. And so we decided to go it alone and set up our own companies. And so we formed a company with Dan Zhu, who was the postdoc who was exploiting this, who was developing this technology, Lewis Yu, who was a third-year research student, and we decided to set up this company. And the first thing we had to do was get a name, because the name is quite important for a company. So we thought up CamGaN for Cambridge Gallium Nitride, and we set that up in 2010. And I was the CEO of the company, and we then talked to lots of people because I had no experience of setting up a company. And a few people said to me, Colin, you may be an okay scientist, but you'll be hoped as a CEO, you've got no experience, you need to find a good CEO. And initially I thought, that can't be right, I can run a company, but after sleeping on it, I realized they were absolutely right. So we got a proper CEO and who did a great job, which I could not have done. So that's another message to give to people here, I think, that, okay, a few academics are really good at running companies, but most of them really are not. And you need to get people with experience of running companies who've got a good track record and then let them take over. And so they got this CEO. And it's an interesting story. So Andrew Lin is a material scientist who was in the department at Cambridge, and he set up his own company and he developed it very successfully. So he got experience. And it helped us, unpaid, he'd given us advice. And so I asked him to be the CEO, and he said, Colin, he said, well, for most people I charge £150,000 a year, but for you, £100,000 a year. So just think of dollars instead of pounds, it's approximately right. And I said, I wouldn't, Andrew, we need to think about that a bit. And at the same time, we'd applied for a research grant from something called the Carbon Trust in England, and which funded research on low carbon technologies. And I got phoned up by a person from the Carbon Trust, and he said, can we come and discuss the research grant with you to see if we can fund it or not? And he came along with another person from the Carbon Trust, and we sat down to discuss this grant proposal. And he said, Colin, he said, we're not actually here to discuss the grant proposal. He said, because I've been so impressed with this, I've come along to say I want to be CEO of this company. And and he brought along someone to be the CFO. And I said, well, how much will you charge? And he said, £120,000 a year. And I said, well, it so happens that just 3 days ago, I had another person who's also very good who said he'd do this for £100,000 a year. And he said he would do it for £80,000 a year then. And so I wasn't trying to play them off because, I wouldn't do that. But it so happened this was a situation we're in. So I went back to Andrew Lim and said, well, we've had someone from the Carbon Trust who's very good, and he'll run the company for £80,000 a year. And Andrew Lin said, I'll do it for £50,000 if I get some shares in the company. And so I said, okay, let's think about that. And I went back to the Carbon Trust person, I said, just for information, and said, we've got £50,000 on the table. And he said, I'll do it for free if I have shares in the company. So I went back to Andrew Lin, and he also said he'd do it for free. And since Andrew, they were both very good people, so it's genuinely hard to choose between them. But because Andrew had been helping us already, I felt, more a moral obligation to him. So we went with Andrew Lin, and so he did it for nothing. And Andrew then said we needed a chief finance officer, and he knew a very good person. And I said, fine, Andrew, but get him for nothing. So he got him for nothing. So I had no idea you could do this sort of effect. But if you set up a company, you can try, just offering shares in a future company rather than providing money for salaries now. I'm not sure if that works in America or not, but it worked in England. So we set up CamGam, and although we believed in the company, none of us really wanted to put our own money in, not at this stage. And of course, we had a research student who had no money, a postdoc who didn't have much money, and I didn't have a lot of money. So we tried not to do that. And we realized the first thing to do was have a company address. And we decided at this stage, we didn't need an office. We could have meetings in my house or meetings in a laboratory. And so we just needed an address. We needed a letterbox. And in Cambridge, there's something called St John's Innovation Centre, which provides a virtual office, and it's £40 a year. I mean, think of $40 a year. It's really cheap. So it's a great bargain. So that was our address, our company address. And it's a virtual address, but letters would be delivered there. And we go every so often and collect letters. I phone up, say, letters come. So that was the idea. And then we registered the company at this address, at Company's House in London. And it's very cheap. It's just £100 to register a company in England. And it's probably the same in America. I don't know, but you will know here. So I was amazed how cheap it is to set up a company in principle. If you get, a CFO for free and CEO for free and these other deals. And so then we had CamGam business cards printed, which we give out to interested people. And then we had discussions again. And in Cambridge, there's a lot of people who help you for free. There's business angels, and they talk to you. And there's other people. And they're all very good. They'll help you for free to a certain extent. And after a time, they'll say, OK, you now have to pay us, or, we now want to get involved. But you get a lot of good free advice. So we were advised to filing a patent's really important, because that shows that you've got some innovative new technology. But we were advised to keep back some important know-how, because if you reveal everything in the patent, there are certain countries who will just use all that information and you have no comeback on them. So we filed a patent, and we did keep back some important know-how. So the patent was a framework of the know-how we had, and then we subsequently filed another patent. And then we set up a website, and that was very important. And again, we were advised we needed professional help because a website is really important. You'll see why in a moment. And so Andrew Lin, our CEO, he said he knew a very good website designer who had had a family and was at home, and she was very keen to get back into business. But he said, I think if I approach her, we can get a good deal from her. And she was very keen to write us a website for virtually nothing, because she would then use this when she went out for a full-time job and saying, this is my recent work. And so she put up a really great website, and again, we paid virtually nothing for that. So we didn't spend a lot of money. And then we started to write a business plan, which was quite difficult because to really exploit the technology, you need 6-inch or 8-inch processing lines, which of course we didn't have. And there aren't many in the UK, and those are owned by other people. So, we were wondering how to write this business plan when people who'd read our website started contacting us. So, and that really amazed us. So we had a significant interest from China, Japan, America, and this company in England called Plessey. And we had the CEOs from these companies came across to Cambridge and chatted with us, and they were all interested in acquiring the company. And it was hard to make a decision, but I made the decision that since the UK had funded, all our research, we should go with the UK if we could. And so we went with the UK company Plessey for 3-month talks. So basically, you get to a stage, you talk to these other companies, then you tentatively choose a company, and then you enter into quite detailed negotiations for typically 3 months. And that's what we did. And then the other companies you didn't talk to. That was in 2011, we had these talks, and it all went really very rapidly, and Plessey acquired both the companies in February 2012, and Cambridge University said this was one of those most rapid acquisitions and exploitations they'd known. Plessey hired 3 postdocs from my group, and one of the things they did was to help to transfer the technology, so that's very important, so they took the patent and the know-how with them to transfer the technology. And people said transferring this technology might take 2 years, but it was transferred in 8 weeks. So that was a very, very rapid transfer. And Plessey sold 2 million LEDs. They're manufacturing now. They sold 2 million of these LEDs in 2014, plan to sell 50 million in 2015, plan to add 400 new jobs by 2017. And they're just selling the chips at the moment, and I'll give you some examples in a further slide. So this is, on the left-hand side is our reactor, which grows on a single 6-inch wafer. Right-hand side, a Plessey commercial scale reactor, which grows on these 7 6-inch wafers. And we transferred that technology across in just 8 weeks. I should say Plessey then had a lot more work to do. We transferred the active region of the gallium nitride LEDs. We didn't transfer any processing because we didn't do the processing ourselves. So Plessey had to develop that. They had no experience of LED growth. They had no experience of gallium nitride before, so they had a very steep learning curve, and they did remarkably well. So this shows some of Plessey products you can go and buy now. I'll just point out on the left-hand side, these are LEDs on metal filaments, which can be used in filament light bulbs, because if people want to have replacement light bulbs, a lot of the public like a light bulb which looks like the old incandescent light bulb, and this looks a bit like it. As you can see the filaments glowing on these light bulbs. Plessey are also making micro LEDs, dot LEDs, which are used in wearables. And you don't know if you're buying a product that's got the Plessey LEDs in, because they're selling these LEDs to a variety of other companies who are then putting them in their products. And the Plessey plan is to expand and to market the total light bulb themselves in the future, and then to expand into power electronic devices. So the Plessey success, so when they acquired us, they raised millions of pounds in those 2-year periods from private investors. These are wealthy families. Again, I had no idea there are these wealthy families around who invest in all sorts of projects. And the first wealthy family was 2 Turkish families, and they've been going for years. And these are the grandchildren who are now investing. and they invest millions of pounds in all sorts of things. They recently bought an airline, and they invested. This is the most scientific thing they've done, and it's long term. It's patient funding. It's wonderful, and they get involved, and they're really interested in the products. So 2 Turkish families, and then some more money came from Russian families, so that they're investing, and then just in September this year, Plessy raised another 60 million, and 30 million was from the Deutsche Bank in Germany, and so it's that additional funding which will enable Plessy to increase its production by 30 times, and they plan to treble employment to over 500 people by 2017. And then just last month, in 2015, Plessy was named Company of the Year by the National Microelectronics Institute. So Plessy are really doing very well. And it's such a pleasure for the people in my group and also myself to see our research exploit our industry in this way. And this is now the final slide, because this is all about innovation. So what I've learned to how to exploit research, and some of these things are obvious, but it's good to remind people perhaps. So what we did was to identify a major need in society. A major need is to reduce energy consumption and reduce the cost of LEDs. And of course that it may be a minor need you find, and that's fine, that's also good. The good thing about a major need is if the market is very large, you only need a small portion of that market to still have a substantial company. So we were lucky that we were working on LEDs. That turns out to be a major need in society. And then you need research funding, and that's really important because you need to take things through to a prototype device stage. Identify a solution, so the solution was GaN on silicon instead of GaN on sapphire. File a patent but keep some know-how, very important. If you're talking to other companies, they really want you to have patents, and if you keep some know-how behind, that puts you in a very strong position. We try to exploit through an existing company. We tried to exploit through several existing companies, and we failed for reasons that these companies hit financial problems. So we decided to set up a new company. In fact, we set up 2 new companies, and that was a lot of fun doing that, and we learned a lot. Obtain a good CEO, really important. So this is a message to academics here. Most of you should set up a company, you should obtain a good CEO, and he makes things happen. He or she makes things happen. Have a good website and business plan, really important. We were lucky. We didn't get to the stage of a business plan because our website was so good. It attracted people internationally who were interested in coming and talking to us. And then this is the final thing to say. This is Winston Churchill. You will hit, although it is great fun setting up a company, you will hit problems you don't expect. So you need to persevere. And Winston Churchill said, never give up, never, never give up, never, never, never give up. And so that's what we found we had to do. So thank you very much.